Hi, I'm Arjit. In this talk, I will be talking about MEDAL, a state distribution matching approach for non-episodic reinforcement learning. To understand why the non-episodic setting is important, consider learning in the real world. A navigation agent may go off-route when trying to reach a goal location. A robot arm tasked with grasping the mug may push the mug off the table. A robot learning how to shelf a book might have to attempt the task several times as it may mess it up. In a more general sense, RL agents need to retry things, possibly several thousand of times. How do RL algorithms contend with the continuity of the real world? Unfortunately, recent RL algorithms have been developed and tested in episodic settings. The agent interacts with the environment for 8 steps and then is reset to a state S naught prime before interacting again. The question is, how does the environment go from state SH to S naught prime? Such resetting of the environment is easy in simulation, where the RL algorithms assume access to nth.reset. But in the real world, humans have to repeatedly intervene into the learning process to reset the environment after every trial, limiting the autonomy and scale of learning. So, what makes non episodic learning challenging? In the episodic setting, when the agent fails to solve the task, it can always retry the task from the initial state distribution. With sufficient tries, the agent is eventually able to learn the optimal goal reaching policy. For the non episodic setting, the agent doesn't get to reset to the initial state distribution. Instead, the agent has to explore from where it last was. This can cause the agent to drift away from the goal state, possibly never reaching it. If the agent does eventually reach the goal, the agent will stay around the goal to maximize the reward collected. This causes the state distribution visited by the agent to collapse around the goal state, which can substantially hurt policy learning. Now we look at how MEDAL does non episodic learning. We assume access to a small set of demonstrations for our algorithm. First, a forward policy tries to solve the task, and then a backward policy tries to bring the agent back to the expert state distribution row star. The forward and backward policies alternately interact with the environment, and the training continues in a cyclic fashion. Why learn a backward policy to match the expert distribution? First, it reduces the exploratory drift that the agent may experience. Second, the backward policy enables the agent to retry the task from different initial state distributions, avoiding the state distribution collapse. Critically, the forward policy tries a task from a wide variety of initial states, some of which are easier to solve the task from and some harder. Overall, this can improve the sample efficiency substantially. More precisely, the forward policy optimizes the conventional RL objective, and the backward policy minimizes the Jensen-Shannon divergence between the state marginal and the expert distribution. How to minimize this divergence? We assume access to the small set of demonstrations which represent samples from the optimal state distribution. Then we learn a classifier where the states from the demonstrations are positives and the states visited by the backward policy are negatives. Finally, the classifier can be used as a reward function for the backward policy to maximize, which sets up a minimax optimization. Now for the results, we evaluate MEDAL on the Earl benchmark. During training, the environment is reset extremely infrequently. The policy learned during training is evaluated on its performance when rolling out from the initial state distribution. First, we consider a mug relocation environment. Consider the performance of a standard RL algorithm when run in the episodic setting and the non episodic setting. There is a substantial drop in performance in the non episodic setting. For all the autonomous RL algorithms we consider next, the forward policies train exactly the same way and they differ only in the objective for the backward policy. A state novelty reward for R3L, a goal reaching reward to the initial state distribution for FBRL, and a goal reaching reward to create a curriculum for the forward policy for VAPRL. Finally, we have our proposed method MEDAL. On harder tasks, we see that MEDAL substantially outperforms all prior state of the art methods. In particular, MEDAL performs close to the episodic setting on the door closing environment and is the only method that gets a non zero performance in the peg insertion task, with over 30% gains above all prior methods. To understand whether matching expert distribution is important, we consider an ablation where the backward policy learns to match the narrow initial state distribution. For two environments here, the blue curve represents MEDAL, where we minimize the divergence to the expert state distribution, and the green curve minimizes the divergence to the initial state distribution. This ablation suggests that matching the demo distribution results in substantial speedup, giving additional evidence for wider initial state distributions. To conclude this talk, we propose MEDAL, a simple and efficient autonomous RL algorithm. The key idea in MEDAL is to keep the agent close to the expert policy state distribution. Additionally, MEDAL results in wider initial state distributions to try the task from, improving the overall efficiency. The code for MEDAL is open source, and more information can be found on the website linked here. Thank you.